You ever stop and think about what's actually going on inside your phone? Like really going on? Well, today we're going to pull back the curtain and look at the actual building blocks of our digital world. And you might be surprised. It all starts with some special material and a couple of really smart ideas. All right, so take a look at this. It looks just insane, right? A total maze of connections. But here's the crazy part. What if I told you that this entire digital universe, it's all built from just a few super simple parts, and they all follow a couple of basic rules? Seriously, let's break it down. So to get to the bottom of this, we have to start small, like atomic level small. We're going to start with a type of material that literally changed the world. Without it, your phone, your computer, none of it would exist. We are, of course, talking about semiconductors. Okay, so why are these things so special? Well, think about it this way. When it comes to electricity, pretty much every material on Earth falls into one of three buckets. You've got insulators, which are like a brick wall to electricity, nothing gets through. Then you have conductors, which are like an open highway, electricity just flows right through. And then you've got this weird middle ground. That's where you find semiconductors. And when I say middle ground, I mean it. But the scale here is just wild. Look at these numbers for resistivity. That's just a fancy word for how much something fights against electricity. A conductor like copper? Basically zero resistance. An insulator, the resistance is astronomical, a 1 with 12 zeros after it. And then you have silicon, the semiconductor, sitting right there in that sweet spot. It's the just right Goldilocks material. So yeah, a semiconductor isn't a great conductor, but it's not a great insulator either. But that's not the magic trick. The real secret, the thing that makes it so powerful, is that we can control its conductivity. We can tweak it. We can tell it how much to conduct and when. And that control, well, that's the key to absolutely everything else we're going to talk about. So how do we get that control? You can't just use pure silicon off the shelf. Nope. You have to kind of hack the material. You give it superpowers. And we do this with a process that has a kind of a weird name. Doping. Yeah, doping. And what it means is we're intentionally adding tiny impurities into the super pure semiconductor. And when I say tiny, I mean it. We're talking about maybe one impurity atom for every 10 million silicon atoms. It's like adding a single grain of salt to a swimming pool. But that one tiny change completely transforms how the material behaves electrically. It's incredible. So this doping process lets us create two different flavors of silicon. First, you can add an impurity that has an extra electron. This creates what we call an N-type semiconductor. N for negative, because, electrons are negative. The other option is to add an impurity that's missing an electron. This creates something we call a hole, basically an empty spot where an electron should be. And we call that a P-type semiconductor. P for positive. Okay, so now we've got our two custom-built materials, N-type with extra electrons and P-type with extra holes. Now, on their own, they're kind of cool. But the real fireworks happen when you stick them together, because when you do that, you can build our very first honest-to-goodness electronic component, the diode. And there it is, the diode. It's literally just a piece of P-type material fused to a piece of N-type material. That spot where they meet is called the PN junction, and that junction is where everything interesting happens. You'll notice the circuit symbol for it even looks like an arrow, and that's a huge clue for what this thing does. Okay, so check this out. The second you put that P and N material together, the free electrons on the N side get a look at all those empty holes on the P side. And they're like, I'm out of here. They jump across the junction to fill in the holes. But this creates a new problem. Right at the junction, you now have a thin layer with no free electrons and no holes. It's a neutral zone, called the depletion region, and it acts like a wall, stopping any more electrons from crossing. But here's the trick. We can control that wall. If we apply some voltage in just the right way, we call it forward bias, we can push the electrons and holes towards the wall, basically shrinking it down to nothing, and poof, current starts flowing. But if we flip the voltage around, reverse bias, we actually pull the electrons and holes away from the wall, making it even bigger and stronger. Now, almost nothing can get through. So what does this all mean? It means a diode is basically an electronic one-way valve. It's a one-way street for electricity. Current can flow through it one way, no problem. But try to go the other way? Nope, the road is closed. And this simple little one-way street is our first big piece of the puzzle. A one-way street is super useful, for sure. But think about it. To build a computer, something that actually has to think and make decisions, a one-way street isn't going to cut it. We need more control. We don't just need a one-way street, we need a traffic light. We need a switch we can flip on and off. And that brings us to the main event, the undisputed champion of modern electronics. You could argue it's the most important invention of the 20th century, period. It's the little thing that makes the device you're watching this on right now even possible. I'm talking, of course, about the transistor. So what is it? Well, the transistor is our second major building block. Remember how the diode was a 2-layer PN combo? The transistor is a 3-layer sandwich. It's either NPN or PNP, and that third layer, that's what gives us a whole new level of godlike control. The best way to think about it is like a water faucet. You have the main pipe where water can flow. The transistor has 2 terminals for a big current to flow through. And then you have the knob on the faucet. That's the third terminal. With just a tiny little twist of your wrist, a tiny electrical signal, you can control the massive flow of water coming out of the pipe. A tiny signal controls a huge flow. You can turn it on, turn it off, or even set it somewhere in between. And for building computers, we use that control in a very specific way. We can use that tiny signal to turn the big current completely off. We call that cutoff. Or we can turn it completely on. We call that saturation. Off or on, a 0 or a 1. And there it is. That's it. We've built a perfect microscopic electronic switch. Okay, so we've got our switch. That's huge. But a single light switch doesn't make a computer, right? So what's the last piece of the puzzle? Well, it's all about how we arrange billions of these little switches to actually create intelligence. And that's where we get into the world of logic. So when we hook up just a few of these transistor switches together in a special arrangement, we create something new. We create a logic gate. And you can think of a logic gate as a tiny little bouncer at a club. It looks at the inputs, the ones and zeros coming in, and based on a very simple rule, it decides what the output should be. Let's take a look at the AND gate, for example. Its rule is super simple. It will only output a 1, meaning it's on, if input A and input B are both 1 at the same time. If even one of them is a 0, the output is 0. That's it. A really basic but super important logical decision. And then there's its cousin, the OR gate. The OR gate is a little more relaxed. Its rule is the output is a 1 if input A or input B is a 1. It could be one or the other or both. As long as at least one input is on, the output is on. Another simple rule, another powerful little decision maker. And here's where your mind gets blown. We don't just use one of these gates. We use billions of them. We link these simple little decision makers together, one after another in incredibly complex patterns. And by doing that, we can build circuits that do amazing things. Circuits that can add numbers, circuits that can store memory, or like you see here, circuits that can pick out one specific piece of information from 4 options. It's all just combining simple rules. So what's the big takeaway here? It's this. The entire, vast, complex digital world, everything from the watch on your wrist to the giant supercomputers modeling the climate, it all boils down to one simple, elegant idea. A microscopic switch. A switch made from a hacked piece of silicon that can either be on or off. That's it. Billions of these tiny switches, flipping on and off millions of times every single second, is what creates everything, literally everything, that we call digital.
Please like, share, and subscribe for appreciation and such more learning friends.